Some other tools that you can use. We have the enclosure rule covered. The next one is consolidation. So this one is just the idea that, let's say I've got a surface here that's emitting, and then I have maybe another surface here, and a third surface here. So let's say I go, and I can't quite, sorry, that's really hard to see, but I don't find in my library of view factors or by other analysis methods that I'm able to evaluate this. But I really want to know how much energy from surface 1 here is hitting surfaces 2 and 3. So what I could do is I can just say, well, I know that light that's being emitted from 1 to 2 and 3 together has to equal that what's hitting that region as a whole. So if I consolidate those two together, I can use that information. So what I mean is I can say F from 1 to the combination of 2 and 3, right, so it's a subscript, is equal to individually F1 to 2 plus F1 to 3. Okay? Maybe it's not entirely clear like why you do this, but let me just we'll step back for a second. So what we're doing, this is like a big game, right? You end up with all these view factors. So let's say you have like 5 surfaces, and you need to compute the radiation exchange between these 5 surfaces. So that means you have 25 view factors that you have to compute. So as you guys know Sudoku, right? The game. It's kind of like that. You're going through, you're filling in a piece of information here and here and here, and eventually you can piece stuff together where you like able to evaluate all the view factors that you need without having to go like run a big expensive simulation or find a library value or something like that. So all these different techniques are ways of like providing that information, those clues that help you then solve for the individual view factors. So this is like one thing you can do. This might be useful to you, right? It's just generally that it's true. Another sort of related thing is something called symmetry. So let's say I have a surface here, and then I've got a surface like this, and then I have another surface like this. Hopefully you guys can see that. This is 1, this is 2, this is 3. And let's say that we know that like there's symmetry involved here, right? So 2 and 3 are exactly symmetric to each other with respect to surface 1. So that just means like if I can compute F1 to 2, I also know that that's equal to F1 to 3 by symmetry, right? Even though like in space they're different, but like hopefully you can kind of see that that's true. The same probability of hitting 2 is shared with 3. So again, you can use that rule. Okay, those are kind of the summary of the rules. There's another one that's not, I wouldn't call it a rule, but it's kind of an interesting thing. Hottel's crossed strings method. I think in the textbook it's called the method of crossed and uncrossed strings. The person who originally developed it was this guy Hottel. And the idea is as follows. So let's say that we have some surface and it looks something like this. And I have another surface and it looks something like this. So I'm concerned with like what's happening in between this space, right? The radiation exchange between these two things. So the idea for this method is if I can know in space where these points are on the ends of the surface, like this. So let's call this A, this B, this D over here, and this C. That is, I know like the X and Y coordinates. So this would be, let's say like X direction. This would be Y direction. I know the coordinates for these 4 points. I can draw lines between these points. So first I'm going to draw from A to D like this, and then from B to C, and then from A to C, and then from D to B like this. And we use the following formula. Then it is A1 times F1 to 2, where this up here is 1, and this down here is 2. A1 times F1 to 2 is equal to actually A2 times F2 to 1. And that's all equal to this. It is the width, so W. W in this case is like into the page, right? So it's like it's a 2D problem. The width into the page times the summation of the length of the cross strings minus the summation of the length of the uncrossed strings divided by 2. Okay, that's it. So I can compute the view factor by adding the cross lengths, subtracting the uncrossed lengths, multiplying by W and dividing by 2. I don't know how you figure this out, but he did. It's kind of interesting. So the way that this would actually play out would look something like this. It would be W times LAC plus LBD minus LAD plus LBC, all divided by 2. Right, the W is multiplying everything out there. Right, that's for this example. So when does this work? This works for 2D problems only. So you have to somehow assume that like the end effects are not important. Like what's happening at the end of the stuff in and out of the page is not important. It works for weird surfaces like this. Like I purposely drew it with a squiggly surface. So the fact that there's a lot more area than just the distance between A and B is irrelevant. Right? It doesn't affect it. There's another interesting case where it still works, and it's kind of mind-boggling. So let's say we have some plate like this. All right, so I've got this plate, and I now move this plate over, like my little animation. I move it over here. And then I draw a dotted line that sort of goes around that, like this. Okay? Now that string A to D is longer than it was before. It still works. Okay, what I mean is the view factor from 1 to 2, accounting for, now we add that longer length, that longer segment A to D, add that in instead of the original, and the view factor is correct. So you're accounting for this like inserted, interfering thing that somehow distorts the length. And it still computes the right view factor. So I think there's a way to prove this, but I don't know how to do it. So any questions on this? This is kind of a cool thing, how you actually apply it. Sometimes there's some nuance to it. But yeah, any questions on it? Okay. I'll just say this other thing. If you find a situation where like, you're computing the view factor, so say you've got a circle like this, and you've got another circle like this, and you want to compute the view factor using this method of strings, you have to do it from like the last place that the string can see. What I mean is you would say like, find the tangent to the circle, and the tangent to the circle here, and the string would have to go from that tangent to the tangent. So your strings, the position you draw the strings, like depends on curvature of the surface. Okay. Question? The area would be the actual extended area. Like if you were to stretch out the area of this squiggly line, it's that. Yeah. Yep, so it's not W times A to B, it's W times the actual length of this segment. Yep.
In the case with the like two semicircles there, would the surface areas just be the surface areas that are in view of each other?
No, it's the total surface area. Yeah, total surface area. So like I said, there's some nuance here to like how you actually apply this. If it's a clear-cut case, like it's pretty easy, you just draw the corners. But if you really want to go down this route, there's some things you kind of got to sort through. But this is as far as we'll talk about it here.